The sun's million-degree mystery. Why is the solar corona so hot? Welcome to Cosmic Enigma, where we unravel the universe's most perplexing questions. Today, we're diving into one of the most enduring mysteries in astrophysics: the sun's impossible paradox. Imagine stepping away from a roaring bonfire. You'd expect the heat to drop, right? But what if the further you walked, the hotter it got? That's precisely the mind-bending paradox at the heart of our very own sun. The sun's visible surface, the photosphere, is incredibly hot, around 5,500 degrees Celsius, 9,900 degrees Fahrenheit. But then just above it lies the solar corona, the sun's ethereal outer atmosphere, which blazes at an astonishing 1 to 2 million degrees Celsius, 1.8 to 3.6 million Fahrenheit. That's hundreds of times hotter than the surface itself. This defies all logic, all the laws of thermodynamics we thought we knew. This is the coronal heating problem. The sun's layers, a journey through extreme temperatures. To understand this cosmic conundrum, let's take a quick tour through the sun's atmospheric layers. The photosphere is the surface we see, where sunlight escapes. It's a churning, boiling cauldron of plasma, marked by sunspots and granules. Temperatures here range from 4,000 Kelvin to 6,500 Kelvin. Above this is the chromosphere, a reddish layer about 2,000 kilometers thick. Here, temperatures already start to climb, from 4,000 Kelvin to 8,000 Kelvin. Next is the transition region, a thin, steep layer, only about 100 kilometers thick, where the temperature skyrockets from 10,000 Kelvin to a staggering 1 million Kelvin. This is where the real mystery begins. Finally, the corona is the outermost, most tenuous layer, extending millions of miles into space. It's made of superheated plasma, a gas so hot that atoms are stripped of their electrons, creating a soup of charged particles. Despite its millions of degrees temperature, the corona is incredibly dim and sparse. Its low density means it radiates relatively little heat, which is why we usually only see it during a total solar eclipse or with specialized instruments. Theory 1. Magnetic reconnection and nanoflares, the tiny explosions. So what's causing this extreme heating? Scientists have two leading theories. The first involves the sun's powerful and constantly shifting magnetic fields. The sun is a giant ball of plasma, and because plasma is made of charged particles, it's intimately linked with magnetic fields. These magnetic fields aren't static. They twist, tangle, and churn. When magnetic field lines, especially those pointing in opposite directions, get too close, they can suddenly break and reconnect into a new configuration. This process, called magnetic reconnection, releases an immense amount of stored magnetic energy, converting it into kinetic and thermal energy for the plasma. Think of it like snapping a stretched rubber band. The energy is released instantly. The brilliant astrophysicist Eugene Parker proposed that countless tiny impulsive magnetic reconnection events happening all over the sun's surface could collectively heat the corona. He called these miniature explosions nanoflares. The energy from these nanoflares is primarily converted into heat through Joule heating, the same principle that heats your toaster. Electric currents generated by the reconnection dissipate, turning magnetic energy directly into heat. To heat a large active region on the sun, we'd need about 1,000 nanoflares per second. For decades, nanoflares were theoretical, too small to observe directly. But in 2014, the Eunice-sounding rocket provided spectral evidence of superheated plasma, consistent with nanoflare activity. And in 2020, scientists observed the complete life cycle of a nanoflare for the first time, showing coronal loops rapidly heating from thousands to millions of degrees in mere tens of seconds. This was a huge step forward in solving the solar corona heating problem. Theory 2. Alphane waves, the hidden force. The second major theory involves a special type of magnetic wave known as Alphane waves. First proposed by Swedish physicist Hannes Alphane in 1942, earning him a Nobel Prize, these are low-frequency oscillations of ions and magnetic fields that travel along the sun's magnetic field lines, carrying energy with them. Think of them like ripples on a pond, but instead of water, it's plasma, and instead of gravity, it's magnetic tension. Alphane waves are generated deep within the sun's convection zone below the photosphere by the turbulent motion of plasma. They then travel upwards through the chromosphere and transition region into the corona. How do they heat the corona? One key mechanism is Landau damping. This occurs when particles in the plasma move at speeds similar to the wave, causing them to gain energy from the wave and convert it into heat. Observational evidence for Alphane waves has been building. In 2007, scientists first observed them traveling towards the corona, though their energy seemed insufficient. But in 2011, more energetic Alphane waves were observed in conjunction with spicules, narrow jets of plasma shooting out from the sun's surface. These waves carried enough energy to sustain the corona's million-degree temperatures. More recently, in 2024, joint observations from NASA's Parker Solar Probe and ESA's Solar Orbiter confirmed that Alphane waves play a crucial role in maintaining the high energy of solar wind jets. Latest discoveries and missions peering closer than ever. The quest to solve the coronal heating problem has been revolutionized by cutting-edge space missions. NASA's Parker Solar Probe is literally touching the sun, providing the most pristine measurements of the corona ever recorded. ESA's Solar Orbiter combines high-resolution imaging with direct measurements of solar wind particles and magnetic fields. These missions have led to incredible breakthroughs. Scientists have discovered widespread jetlets, tiny fleeting jets of hot plasma created by small-scale magnetic reconnection at the base of the corona. Surprisingly, these jetlets contribute to both the fast and slow solar wind, the continuous stream of plasma flowing from the sun. This was a major surprise, as the origin of the slow solar wind was previously elusive. Other recent findings include serpentine structures in the photosphere's magnetic field, which could provide more opportunities for magnetic reconnection and energy release. And the Japanese Hinode satellite has observed active filamentary structures and magnetic waves in the corona, further highlighting the complexity of the problem. Why this matters, space weather, and beyond. Solving the coronal heating problem isn't just about satisfying scientific curiosity. It has profound implications for us right here on Earth. The sun's corona is the birthplace of the solar wind and powerful events like coronal mass ejections, CMEs. CMEs are massive eruptions of magnetized plasma that can hurl billions of tons of material into space at millions of miles per hour. When these solar outbursts collide with Earth's magnetic field, they can cause space weather. This can lead to damage to satellites, disrupting GPS and communications, widespread power grid blackouts, disruptions to shortwave radio and military communications, and radiation hazards for astronauts. By understanding how the corona gets so hot and how magnetic reconnection and Alphane waves drive these phenomena, we can better predict space weather events. Improved forecasts mean we can take protective measures, safeguarding our technology and infrastructure. Furthermore, our sun is a typical star. Insights gained from solving its coronal heating problem can be applied to understanding the atmospheres and behavior of countless other stars across the universe. Conclusion and future outlook. The sun's coronal heating problem remains a captivating mystery, but we're closer than ever to unraveling it. It's likely that a combination of magnetic reconnection, nanoflares, and Alphane waves, along with other mechanisms, are all at play. The future of solar physics is bright. Missions like Parker Solar Probe and Solar Orbiter will continue to send back unprecedented data, and upcoming ground-based telescopes, like the 4-meter European Solar Telescope (EST), will allow us to observe the sun's magnetic field and tiny events like nanoflares with incredible detail. The sun is a dynamic, powerful star, and every new discovery helps us protect our planet and deepen our understanding of the cosmos.